right, so we're going to continue with chapter 15. So we talked about how we can find the pressure by adding the atmospheric pressure and plus this rho g times h and h or d. So, so then this equation, sometimes the pressure on the left side is known as the absolute pressure, and then you have the atmospheric pressure. And then one of the things we can do here is then this is known as a, as I mentioned, gauge pressure. So then gauge pressure, the PG, right, is equal to then the difference between absolute and atmospheric pressure. So that means the gauge pressure is the difference between absolute and atmospheric pressure. And a lot of times whenever we're using, let's say something, like let's say a gauge pressure to measure the tire pressure, what we're actually measuring is the pressure, difference between inside and outside, which is basically the pressure gauge or the gauge pressure. So that means, over here, this reading is the pressure difference rather than the pressure inside the tires. All right. So for the hydrostatics, so basically we are, as I said, right, dealing with the hydrostatic equilibrium. And most of the time, let's say here, draw a picture, show if the surface, is open to the atmosphere or if it's not, determine the pressure at the surfaces. If it's open to the atmosphere, then there's atmospheric pressure at the top. If it's, the surface covered by gas, then we can just say that pressure is the gas. If it's, the closed surface, then pressure equals F over A, where F is the force the surface, such as piston, exerts on the fluid. Okay. Remember the horizontal line, right? The pressure along the same horizontal line is always, the same pressure. And also we have the gauge pressure, which is the absolute pressure minus 1 atm. And we can use the hydrostatic pressure equation, which is basically absolute pressure equals atmospheric pressure of P0, 0.1. So let's say if you have a container, so let's say at any 2 point, let's say 0.1, 0.2, then let's say you can say pressure at 0.2 equals pressure at 0.1 plus rho gh, where h is the height difference between 0.1 and 0.2. All right, so we also have a lot of instruments that can be used to measure pressure, and manometers are one of those instruments. And there are again number of instruments that we can use. So this one is used, for example, to measure pressure for some unknown gas. So you can see, right, it's a U-shaped tube connected to the gas at one end and open to the air at the other end. So tube is filled with liquid mercury of density rho. And what we have here is, let's say you can measure the pressure at point 2, for example, by simply assuming that at the top, there's atmospheric pressure. And what we can do here is if we measure the height h, that's because this is the this point 1 is the boundary between a gas and a liquid. So along the horizontal line, then we can measure the pressure at point 2, which is easy for us because we say pressure at point 2 is equals to atmospheric pressure at the top here, right? Then plus rho g times h, which is the rho of the fluid, times g times this height h. So we can find the pressure at point 2. Once we find the pressure at point 2, that's exactly the same pressure at point 1. That means the gas pressure is same as pressure at point 2, which is 1 atm or atmospheric pressure plus this rho gh. Okay, because the pressure point 1 and 2 are exactly the same because they're along the same horizontal line. All right, so another one is barometers. So this one is basically used to measure the atmospheric pressure. So you can see, right, you show a glass tube sealed at the bottom and filled with the liquid. So we seal the top and invert the tube. Okay, invert the tube, place in it an open container of the same liquid and remove the seal. So this device is basically allows us to measure the pressure, let's say at point 2, and then we have basically the same pressure at point 1, because here inside we end up having pretty much a vacuum, which is basically zero pressure. So we can measure the height of the liquid in the tube, right, and measure the pressure basically at point 1 and point 2. So point 2 is just rho gh, and point 1 here is basically an atmospheric pressure. So that means we can this allows us to measure that atmospheric pressure. All right, so this table gives us many different units of the pressure. I mentioned that pressure has a SI unit of Pascal, which is kind of equivalent to Newton per square meter. But there's also, atmosphere or ATM can be used when dealing with mostly, let's say, atmospheric pressure. And then we have also millimeters of mercury, or inches of mercury, or pounds per square inch, and so on and so forth. There are a lot of different basically measurements. So these are then all of those measurements, um, conversion to basically one ATM. That means how each measurement or each different unit for pressure can be converted to ATM. And then, once you have the ATM equivalent, you can also basically convert it to Pascal. For example, 14.7 psi is equals to 1 ATM. But this is also equals to 1.013 times 10 to the 5 Pascal. So then you can go from psi to Pascal, and you know any other unit into the Pascal and things like that, because all of those pressures, right? So 760 millimeter of of mercury, or 79.92 inches of mercury, they're all equals to 1 ATM, and so is 100,000 Pascal roughly. All right, so again, here more complete, because you can also have a torr, you can have a centimeter of mercury, you can have pound per square inch, pound per square feet, right? And so on and so forth. There's a bar, there's a, all those different type of units for mercury, units for the pressure. As you can see, right? You can have plenty of applications, right? So that uses this concept of pressure. All right. So one of the things we have here is this is known as a Pascal's principle, or Pascal's law, and this deals with generally a liquid, or fluid that is basically enclosed in some kind of a system. So let's say it could be enclosed in a tube, or in let's say, for example, your toothpaste, right, enclosed in a container. So let's say when you press at any part of your toothpaste, right? So that basically all that pressure transmits everywhere. The idea for the Pascal's principle is this: if you have an enclosed fluid, then the change in pressure or variation in pressure transmits everywhere without changing or diminishing its magnitude. So for example, then hydraulic lift are a very good example of that. So hydraulic lift includes some kind of fluid that is enclosed within two pistons. So let's say here's you have a piston one, here's you have piston two. The idea here is that by having then some kind of liquid with density that connects this, let's say point one and point two, or pressure, let's say, so for example, like point one, then you can say there's a piston one that we can use to apply downward force F1, and then let's say, for example, this is being your second piston, right? Then it allows pretty much to exert force, let's say, sort of like, let's say, output force, right? Could be in the opposite direction to lift the car. So that, for example, this hydraulic lift is used to lift your car at the repair shop, and it's a relatively simple idea. So for example, if you have let's say this point one to be where your first piston is, so then you apply force F1. Okay, that means the pressure point one is equals to F1 over A1. And then you have point two, which, remember, will be equals to the pressure two, right? Because there are pressure one, which is exactly same horizontal line. That means the pressure two is equals to the pressure one. But also there's a height h, so then there's a also this rho gh times a2, which is rho gh is the gauge pressure, a2 is then the force. So the idea here is then this f2 as a force, which is what we have here is, you can say that uh, pressure one is equals to pressure two, which means then f1 over a1 is equals to f2 over a2. But then there's also an extra pressure, right, because of the height difference. So then you can say that there's also becomes a factor there, which basically you can say then this is plus, this, I can say this, the extra force acting over there, extra force over that area. Okay. Now, if you combine this, and then you get basically this equation over here. So you have then F2 is equals to, so if you rearrange those, so let's say if you kind of like just look at those two, which is finding at point 2, so then you have like, let's say since they have the same pressure, then you can say F2 is equals to then, you know, A2 over A1 times F1, but then minus this rho GH times A2, which is basically the force act, that extra force that we have because of that, extra liquid above. And then you can find, for example, then F of 2. F of 2 is then basically the output force. And a lot of times that output force can be greatly modified if we, for example, change that, let's say, the area 2 compared to area 1. See, if area 2 is much larger than area 1, then what you get here is you get, for example, F of 2 is equals to, let's say area 2 is 100 times greater than area 1. So area 2 is 100 times area 1, divided by area 1 times force 1. So then you can see then F2 is equal to then 100 times force 1. That means by applying, let's say, for example, 10 newtons here, then you can get 1,000 newtons as an output, even if you, let's say, take out a little bit of, let's say, extra force that goes into, let's say, lifting a little extra distance. This is not enough to give you, let's say, much, much greater output force. So maybe like, let's say 800 newtons or something like that when you apply only, let's say, a 10 newtons. This could be like, let's say the difference between A1 and A2 can be 1,000 times or, even more. So then you get much, much greater, for example, output force. All right. So again, kind of looking at this hydraulic lift, right? So suppose we need to lift the car higher. So if the piston 2 is pushed down a distance D1, the car is lifted higher by a distance D2. Okay, so then basically, this is D1, D2, and then again, you can kind of rearrange this equation and use it to calculate, the distance D2 if you are, let's say, moving the piston 1 down by the distance, D1. That's because, the piston 1 is much easier to, let's say, press it down because it just basically has a small cross-sectional area. So, less force will go into like, pushing it down. And but on the other side, let's say you have a car over there, right? So then just a little bit of force is able to lift basically a very heavy car on the other side. All right. So the next concept that we're going to talk about is the buoyant force. So this is a new type of force, and this force generally is present in liquids or gas, so that's why it's in fluids, but it's much stronger in liquids compared to in gas. So whenever you talk about buoyant force in, let's say in gas, generally it has to be, let's say relatively, a light object like a balloon or something like that for that buoyant force to, be strong enough that it can overcome, let's say, gravitational force, something like that. Because gravitational force is already, let's say, a strong force because you take the mass times 9.8. So then the buoyant force for the, gas molecules, right, is very light, very small. So then gravity is, is able to, let's say, a lot of times overcome the buoyant force. But buoyant force becomes much stronger in liquid. So, and then a lot of times that buoyant force is significant, a factor. So that's something that, let's say, we're going to be looking at, next few slides. So for example, if you take a beach ball and submerge the beach ball into the water, right? Let's say you're in a pool, take the beach ball, submerge it into water. See, when you let go, the gravity is not pulling it all the way to the bottom of the pool. You let go of the beach ball, it's actually beach ball seems like it's being pushed upward, right? Who pushes upward? There's like nobody there, right? But it's actually pushed upward, it starts floating. Well, that's because this buoyant force from the liquid exerts upward force on the beach ball, and basically the beach ball is basically pushed upward and starts floating. Try to do that with a bowling ball. You put the bowling ball into the water, let go, well, it's going to go down and sink. So how come then it's not like a beach ball pushed upward and starts floating? Well, it's still being pushed upward by a buoyant force, but because of its heaviness, the gravity is much stronger, so it's able to, easily overcome the buoyant force. But beach ball, because of gravitational force on a beach ball is much weaker, right? Because the beach ball is basically very light, the buoyant force is relatively stronger. So we're gonna see, right? Technically, um, same size beach ball and gravitation, so beach ball and the bowling ball will have exactly same buoyant force acting on them, but we're obviously going to have a different gravitational force because of the difference in the mass. All right, so let's look at again. So here's sort of like, let's say, deriving those equations for the let's say buoyant force first. So you have an object completely like completely submerged in water. So again, we know that going down you have an increasing pressure. That means if you look at this cylinder inside, so you have a force, the molecule, water molecules acting at the top of the cylinder, and then at the bottom of the cylinder, we know one thing, that bottom, the force is stronger than the top force. Why? Because the pressure is stronger at the bottom. That means this is you know uh, closer to the surface than the bottom part, so there is a stronger downward a force acting from the bottom part. So then we can say that there's a downward F down and then F up. So then if you do F up minus F of down, well, there's going to be net force. And net force is what the buoyant force is equals to. So the buoyant force is the difference between upward and downward forces for an object that is fully submerged. Okay. So this is known again as a buoyant force. And we're going to put F sub B representing that buoyant force. All right. So now the buoyant force is generally due to the fact that when you submerge an object into the water, let's say here's a let's say a container with some water, and then when you submerge an object, so let's say you submerge an object, well, this object basically now occupies the same space as the water was occupying before the object was submerged, because where the object is right now, there is no longer water there. So where's the water? Well, it's been pushed upward, so the water level rises. And then what we can say is there's when you submerge something into the water, it displaces certain amount of water. Okay, and then if I take that amount of water that has been displaced, that means only the amount of water that has been displaced, find its weight, so the weight of the displaced water, this is what the buoyant force then is equals to. So the buoyant force, okay, is basically equals to the weight of the displaced, object, displaced water. Okay. Now, also one of the things we can see is that, for example, if you have the object right submerged, then you right away have two forces acting on it. There's a gravitational force downward, and then the buoyant force upward. Okay, so the buoyant force, so input like F of B, always going to be upward, acting toward the, let's say, toward the surface. Okay, so now this force, basically in magnitude, is equal to the weight of the displaced fluid. That means this is equals to mass of the displaced fluid times G. Let me put like just a M displaced like this, because it's not equal to the entire weight of the liquid, but just the that small portion that has been displaced when you submerge the object into the water. Okay, that means in terms of then the buoyant force, I have the mass of the displaced fluid times G. Well, one thing we talked about last time is that whenever there is a mass, we would like to replace it with the density times volume. So that I can replace this with the density of the fluid times volume of the displaced fluid, then times G. That means I can write it in terms of this. Okay. So again, when the object or portion of the object is immersed in fluid, it is displaced as fluid. The displaced fluid's volume then equals to the volume of the portion of the object that is immersed in the fluid. Okay, so this is actually been discovered by Archimedes. So Archimedes' principle then states that a fluid exerts an upward buoyant force F of B on an object immersed in or floating on the fluid. The magnitude of the buoyant force equals the weight of the fluid displaced by the object. Okay, that means one thing we can do here is that suppose if the fluid has a density rho F, which is the raw fluid, and the object displaces volume Vf, which is the volume of the fluid displaced, then Archimedes' principle in in equation form is, basically this is the weight, right? So remember, weight is mass times gravity, but we write mass in terms of the density times volume. So the density times volume. So the density of the fluid times volume of the displaced fluid times 9.8. All right. So then one thing we have here is the Archimedes obviously did not put this in the form of, let's say, buoyant force, right? But one of the things he did he recognized that when you have a container with water and then you submerged, an object into the water, okay, then it basically displaces a certain amount of fluid. Okay, but what his let's say the important discovery the Archimedes did to recognize connection between the displaced fluid with the object that is actually is into the water, is submerged into the water. And there's a really nice legend about that. So basically the legend is that Archimedes, who was basically a Greek engineer pretty much, living in city Syracuse, which is now the Sicily. So basically the king was just like all the other kings. He had a lot of money and he wanted to do something, let's say, something fancy for himself. So he decided to hire someone and have him make a crown of pure gold. So basically, he gave this guy a lot of gold and said, okay, so take this all, take this gold and make me a crown of pure gold. All right. So after a while, the guy made the crown and gave it to the king. So then let's say the king, got the crown, was wearing it and was happy until one day he got suspicious. Like, what if this crown is not pure gold? What if the guy cheated and took some of the gold and replaced it with the cheap metals and things like that? And now I'm not wearing a crown of pure gold. All right. So um, he, basically had Archimedes, to figure out if this is, a pure gold or not. So that means Archimedes had to figure out if the crown is pure gold or not. All right. So one of the things, obviously, Archimedes knew is that, if you have a, object, you take its, mass and take its volume. So the sorry, the ratio of mass over volume will give you the what we call density. So then he can compare, right? If this density, or this ratio is exactly the same if he takes another like small piece of gold and find its mass and its volume and look at the ratio, regardless of the size or shape of the, let's say, piece of gold, that the ratio mass over volume will exactly be the same. So let's say you take this cube and you take a sphere, find the mass and volume of each one of them, find the ratio, you're going to get basically exactly the same ratio. So that means all he had to do here is, find the mass and the volume of the crown, and then he could find then basically the density or the ratio of that, crown, and to see if it's, matches the density of a, let's say, a pure gold. The problem was that the crown, even though it was easy to get the mass, it was much harder to get the volume correctly because it's not like a regular shape. It's not a cube. It's not a sphere. It's not a rectangle, right? So that means he had to, I don't know, let's say something like this, right? So that means it's an irregular shape, and he had to try to find the volume that correctly. Um, so he struggled with that initially until one day he was taking a bath. He got naked, got into a bathtub, and then he realized when he got into the into the water, he realized that when the water level rises, it is directly proportional to the volume of his body. That means his brilliance was that he recognized that the volume of the displaced fluid, so the volume of the fluid is exactly equal to the volume of the object. Okay, so that's basically what Archimedes' technical is principle actually represents, is that when you submerge an object into the water, it displaces a certain amount of water, but how much it is displaced is independent of the weight of the object. It only depends on its volume. That means this could be a beach ball or a bowling ball. As long as they're the same size, they displace exactly the same amount of water. Even the bowling ball may be like 100 times heavier. But volume of the displaced fluid is equal to the volume of the object. That means we can, you know, we can do an experiment. Basically, that's what he did, right? He, let's say, had a container with, fully with, with water, and then he put this inside another container that can collect that water, right? Something like this, maybe. Then he put the crown inside, so then he had the water, water level go up. So then, water was then collected in another container. How much was, displaced, and then he just easily measured the volume of the displaced fluid. Once he found the volume of the displaced fluid, then he had the volume of the crown. You have the volume of the crown, then you do mass of the crown over the volume of the crown. You have then the density. And obviously, once he calculated the density of the crown was not of pure gold, obviously, and he was able to prove that the guy indeed cheated and got the uh, some of the gold replaced with cheap metals. So the density, right, that ratio is way less than actual gold. So obviously, you didn't want to be that guy, who made the crown at that time. All right. Anyway, so that's kind of like the idea of this discovery, that he was able to, come up with this, discovery of that volume of the displaced fluid exactly equals to the volume of the object. Okay. And that's not necessarily only his discovery. He also invented water pump, the screw, and, number of other things. So it was really probably one of the best, minds in the ancient Greek. And he was probably the first engineer. You can think of it like that. So, all right. So here's an example. So you have a 70-kilogram ancient statue lies at the bottom of the sea. Its volume is 3 times 10 to the 4 cubic centimeters. How much force is needed to lift it? All right. So, all right. So we're given the mass of the statue, which is 70 kilograms. That means what we can do here, we can calculate the gravitational force, which is mg. So we can calculate this to be 70 kilograms times 9.8, and this is equals to this is 690 newtons. Okay, then this the as you can see, right, this is like free body diagram. The idea that amount of force needed to lift is equals to then the difference, let's say you can say, right, the net force in the y direction equals to this F plus F of B, which is the buoyant force, then minus mg. That means this amount of force is equals to then the difference between then mg minus then the buoyant force. Okay. So all right, so we got the mg, which is 690 newtons. Then next we'll need to find then the buoyant force. All right, so then the buoyant force is equals to the weight, let's say, of that displaced fluid, which is mass of the fluid times g. But we know that we can just replace the mass with the density of the fluid times volume of the fluid times g. Now, we don't know how much volume was, we're not given how much volume was displaced, but we know the volume of the statue. And then we know the Archimedes principle says that the volume of the fluid, displaced fluid, is equal to the volume of the object. That means it's equal to the density of the fluid times the volume of the object times g. So then we can calculate the buoyant force from here. It's water, so it's 1,000 kilogram per cubic meters in terms of its density. Um, well, it's actually bottom of the sea, so we should use this 1030 kilogram per cubic meter because it's salt water. Then times then the volume of the object, which is 3 times 10 to the 4 cubic centimeters, which means then we have to say it's 1 over 100 centimeters, the whole thing cubed, right? So then, we can cancel that. And times 9.8 meters per second. So then I can calculate then the buoyant force to be roughly 300 newtons. Then this force is going to be equals to the 690 newtons minus 300 newtons. So here more or less 390 newtons. Okay. So that means 390 newtons is needed to lift the object or the statue, right? assuming that there's, it's in the liquid and there is basically, we have to overcome this also, the gravitational force. Okay, that means the idea was that, we needed, combined something that at least equals to that the gravitational force, so it can be lifted without accelerating, lifted upward. Because the idea was that, this net force equals zero because we're going to be lifting it at the, dynamic equilibrium, right? It is moving without accelerating, so it's being lifted upward. All right, so here's another example, which is kind of similar in terms of finding a density of the crown. So this is kind of like the, let's say more modern version of this crown, the crown legend that I just told you. So things like this. So one thing we can do is we can, find the weight of the, or the mass of the crown when you measure it, in air. Because when you're measuring in air, this reading is actually the reading of the tension force. Okay. So, but if you have just the, the crown in air, the forces acting on the crown is the gravitational force downward and the tension force upward. So then the F of t minus, let's say, F of g is equals to zero because it's just hanging. That means F of t is equals to then F of g. That means the tension force is basically equal to the weight. That means if this is measuring in terms of the value, right? So which is basically the mass times g. So the mass is 14.7 kilograms, means that in a way it measures, actual, the mass of the, let's say, of the crown. So this is known as the actual mass or actual weight. If we repeat this experiment where crown is submerged in water, then suddenly what we will see here is the reading is actually different. Because in this case, F of t then plus buoyant force, because there's a buoyant force, minus F of g equals zero. That means this reading is equal to the difference between gravitational force and the buoyant force. I put like a F of b. I'm just used to putting like b for the buoyant force. All right, so F of b. Okay, so it's difference between them. Okay. That means this is known as apparent weight. So W. So this is apparent, or W apparent. So the apparent weight. That means you think like this: actual weight is then 14.7 times g. Apparent weight is 13.4 g. G means that times 9.8. That's what I mean. Times 9.8. Okay. Now the question is that, is the crown made of pure gold or not? Well, one thing we can see here is this. So in order for us to get that, we need to, first find the buoyant force. Buoyant force, as you can see, right, then is the difference between, actual weight and apparent weight. Because this is, let's say, apparent weight, values is the actual weight, and the buoyant force basically ends up being the difference between them. So this is then 14.7 g minus 13.4 g, right? That means the buoyant force now is just, 1.3 times g, or 1.3 kilograms times then 9.8. So basically that's what it's, equals to. That means in a way that, you can say that buoyant force, remember, it's the difference between, actual weight minus the apparent weight. We also know that the buoyant force is equals to then the weight of the displaced fluid, which is equal to the density of the fluid times volume of the fluid times g. Okay, so this is basically that equation that we have. That means there are two equations for the buoyant force. One is from the difference between actual and apparent weights. The other one from the, weight of the displaced fluid. Okay, and in a way, one thing we're gonna do, we're gonna combine that, because, then I can say then W minus W prime is equals to density of the fluid times volume of the fluid times G, because that's, both of them are equal to the buoyant force. All right, so one of the things we have here is that from here, we don't see any information about the density of the gold. Well, one thing I have here is this. Density of the gold, here's the equation, or the density of the crown, let me see, the density of the crown is equal to the mass of the crown divided by its volume of the crown. Well, we do have the mass of the crown, which is its actual mass, right? 14.7. But one thing we don't have is the volume of the crown. How do we get the volume of the crown? Well, from this equation, because I have the volume of the fluid, but again, what Archimedes discovered that is exactly the same as the volume of the object. So I can come back and replace that with volume of the object, and then I can rewrite as volume of the object is equals to the difference between actual and apparent weight divided by density of the fluid times G. And then replace this in this equation. This is basically volume of the crown, right? The object is the crown. That means it's equals to mass of the crown divided by that, which is end up W minus W prime, then times the rho of the fluid times G. So then we can calculate the density of the crown, which is 14.7 kilograms times 1000 kilograms per cubic meters for the water, then times 9.8. Then this is basically 14.7 G minus 13.4 G, which means I can factor out G in a way and say this is then 9.8, and then even cancel the 9.8 from both sides. Okay. So if we calculate then the density, what we're going to get here is 11.3. Well, let me see. So 11.3, or you can say like, okay, so I kind of don't have room over here. Let me write it over here. So the density of the crown is 11,300 kilogram per cubic meters. Okay. So this is definitely not same as the gold, because gold has a density of roughly 19,000 kilogram per cubic meters. That means definitely this is not made of gold. So that's kind of like another way of finding the density of the crown. All right. Oh, there's a table where I kind of write down the values for the densities, so you can see, right? So the gold is right here, which is 11.93. Sorry, 19.3. Remember, we got 11.3. It's kind of like kind of equal to lead. That means maybe most of the crown was made of lead, right? And just maybe a little bit of it is let's say gold, or maybe it was coupled with aluminum, I don't know, iron and copper and things like that. So that means it's possible to have a surface made of gold, but everything inside is pretty much cheap metals. All right, so now one of the things we can talk about here is this: if you have an object that is fully submerged, is it going to float, or is it going to sink, or is it going to just sit there? Depends at the end of the day on the density of the object relative to the density of the fluid it's in. Because one thing we have here is this: so when you have an object that is fully submerged, so you can see, right? So if you have a container and you submerge the object, there are two forces acting on it. So there's a buoyant force upward, and then the gravity downward. So then this is basically buoyant force minus then the gravitational force. So buoyant force is rho of the fluid times volume of the object, volume of the fluid, then times G. And this is then minus the weight of the object, which is mass of the object times G. But I can rewrite the mass of the object in terms of, so the buoyant force is density of the fluid, volume of the fluid times G, and object mass will be replaced with the density of the object times volume of the object times G. Okay. Now, again, using the Archimedes principle where volume of the object equals volume of the fluid, I can rewrite then this difference in terms of by replacing volume of the fluid with the volume of the object. And I can see, right, I can factor out G times volume of the object. And what I end up with this. So density of the fluid minus density of the object. That means in order for the object to sink or float or just have a neutral buoyancy, you have to look at the object density relative to the water density or the fluid density. See, if the average density of the object, and we call it average density because let's say it might be irregular shape and things like that, so you can average out the density, or let's say not uniform density. So the average density of the object. If average density of the object is greater than density of the fluid, then the gravitational force That means, see, this is where the density of the object here is this density of the fluid. If object density is greater, right, then downward force is stronger, so then object basically gonna sink. Okay, so object sinks if the average density of the object greater than density of water or fluid. If actually the object density average is less than density of the fluid, then it's gonna float. It's gonna pushed upward and start floating in the surface. In order for the object to have a neutral buoyancy, then density of the object should be equal to density of the fluid. And then you have again, it's average, but you're gonna have then neutral buoyancy. That means this, if they're equal, then you get zero, which means that there's no net force, not upward or downward, and object is in static equilibrium, so hydrostatic equilibrium. So that's what we have. The difference between densities for the object and the water, right, will determine if the object sinks or floats. So that's why, for example, um, wood, which has a less density than water, right, a lower density, is being pushed upward and floats. Beach ball has lower density than water, pushed upward and starts floating. But for example, bowling ball or a copper ball or whatever, right, something that has a large let's say density, or like will then have a greater gravitational force than a buoyant force, so they will go ahead and sink. Okay, now again, because this object is fully submerged, I could use the fact that volume of the object is equal to volume of the displaced fluid. Okay, this works when the object is fully submerged. But for example, what if object is floating and not fully submerged? Is that this volume of the displaced fluid, let's say, is equal to the volume of the object? Well, no, it's not equal to that, because see, not all the volume of the object is inside the fluid. In that case, what we can do here, we can say that volume of the fluid displaced by a floating object of uniform density is, let's say, if you have a buoyant force, density of the fluid times volume of the fluid times g equals mass of the object times g, then equals density of the object times volume of the object times g. Because if the object is floating, then buoyant force is exactly equals to the gravitational force. Okay, that means what we're saying here is it is neutral, let's say buoyancy, right? So that those two are equal to one another. That means density of the fluid times volume of the fluid times g equals to density of the object times volume of the object times g, which is basically saying buoyant force is equal to the gravitational force, but then rewriting everything in terms of densities and volumes and things like that. From here we can cancel the g from both sides, and then we have then product of density time or and density and volume of the fluid equals to the product of density and volume of the object. And then from here I can say divide both sides by density of the a fluid, and then we have this equation: volume of the fluid equals the ratio of the density of the object over density of the fluid times volume of the object. And it's always going to be less than volume of the object, because volume of the fluid equals the volume of the object when it's fully submerged. Well, fully submerged. But if it's partially submerged, this is no longer equal to one another. Okay, so that's kind of like that. And you have to use then this equation. Here's an example. So most icebergs break off glaciers and are freshwater ice with a density of 917 kilogram per cubic meters. All right. So density of seawater is then 10,030 kilogram per cubic meter. So that's why the water, let's say the iceberg, right? So the ice is actually floating because it has a lower density than, a seawater. And because it is partially, a floating, then we can use this equation: volume of the fluid times the, density of the fluid equals volume of the object times density of the object. And then we can say volume of the fluid that it, let's say is being displaced is equals to then the density of the object over density of the fluid times then volume of the object. So one thing we can see here is this: volume of the fluid then that is being displaced by this iceberg is then the density of the iceberg, right, divided by density of the seawater times volume of the object. Okay, And one thing we see here is 0.89 of the volume of the object, which means 89% of the volume of an iceberg is underwater. Okay, so you only see about 11% of the iceberg. 89% of it is underwater. Okay, so that's why what we can see here is, you know, amount of the volume that is displaced is equal to the 89% of the volume of the object. But what we can see here is the floating part, which is not in water, right? And that's only the 11% of the iceberg. All right. So the same way we can look at sort of like the boats, right? So you can see the figure shows the basic model of a boat. The boat will float if the weight of the displaced water equals the weight of the boat. Okay. And again, because what we have here is, because if you're floating, right, then the buoyant force and the gravitational force are equal to one another. Okay, in this case, the boat will float if the weight of the displaced water, which is the buoyant force, remember, buoyant force is always equal to the weight of the displaced water, equals the weight of the boat. Okay. Now, from here, we can look at in terms of, let's say, this, a boat having like a rectangle, sides of, height h, and then the solid bottom of the mass m naught equals area A, right? So basically what we can do, minimum height of the sides then is equals to h minimum equals to the mass of the object divided by density of the fluid, times, the area. And then this is what, we get this from using exactly the same equation where the buoyant force, which is weight of the displaced fluid, equals the gravitational force of the object. Buoyant force, remember, is density of the fluid times volume of the fluid times g. And then gravitational force is then given in terms of the density of the, or let me write it in terms like a mass of the objects times g. Just basically, we can just leave it in terms of that. Now, if you then looking at in terms of, let's say, amount of water, right, that we have, this, displays, right? So then we can say that this is equals to, so then the density of the fluid. So, the volume, remember, volume will be, can be written as area times height, right? So area times height. So then, in terms of density of the fluid times height times area, I can cancel the g from both sides, and this is equals to mass of the object. And then we divide, both sides by density of the fluid times area, and then not the height, so you can see it like this, and then we end up with this. That means this is then at the minimum height. That means, right, so you don't want, like, let's say, the entire boat to be underwater, right? So that means minimum height. So then you still have, some parts of the, boat floating, right, will be given in terms of this equation. So mass of the object divided by the density of the fluid, then times the area. All right. So now we go to the second part of the fluids that I'm going to cover, which is moving fluids. So this is basically known as fluid dynamics. So we covered hydrostatic, equilibrium, right? That means the hydrostatic means the fluid at rest. Now this one is going to be then moving fluids. And moving fluids generally are very, very complicated. If you're an engineer, kind of go into this type of field, you're going to have to take entire class on fluid dynamics. So, and the fluid dynamics is relatively complicated because there are a lot of things have to be taken into account. So we're going to have to, since we're giving you just a, basic introduction, we're going to have to like simplify quite a lot. And the simplification or assumptions that we're going to make is this: the fluid is incompressible. It is more like a liquid than a gas. That means, we're considering it's, remember, you can compress the gas, but you cannot compress liquid. That means what we say here is, you cannot compress, the fluid in this particular model that we're using. So it's an ideal fluid model. The fluid is non-viscous. It is more like water than syrup. That means if you have a flowing, let's say a fluid, it is more like a water. That means, let's say, any layer of the water moving at the same speed. But if you have, for example, a syrup, right, then if it's flowing, then the parts that, because of syrup, right, the parts basically that at the bottom moving slower than the parts at the top, which are moving faster. That means you have a non-uniform flow rate. So here we want to say that, it's more like a uniform flow rate. And the flow is steady. It is more like laminar flow than a turbulent flow. So we're going to look at an example of a laminar and a turbulent. And this is also because turbulent flow is pretty much, unpredictable. You cannot really predict where the turbulent flow can be moving. So let's say here's an example for that. So you can see the rising smoke in the photograph begins as a laminar flow. That means, see, when it's moving, you can say, okay, right now it's here. Some later time it's going to be over there, right? It's kind of like a more or less following a straight line. So same as here. It's going from there to there. Here is kind of a straight line. But as soon as it gets here, you just can't go anywhere, right? Because this all region here is a turbulent flow. So it's very random motion. It can go any direction depending on, many different factors. So we're going to then assume that we're going to be dealing with just a laminar flow. That means we can easily predict, and calculate the motion of the fluid. All right, so you can see, right, the laminar airflow around a car in a wind tunnel is made visible with a smoke. Each smoke trail represents a streamline. And you can see, right, those streamlines, they don't, cross each other. So we can then use them basically to, if you, let's say mechanical engineer and things like that, or, let's say, aerospace engineer, right? So that's, something that you're going to be really studying in quite a detail. Here we just, idea is that we're simplifying and assuming that we are dealing with just a laminar, flow like this. All right. So when then taking all those three assumptions, when then the liquid, right, most like liquid, water like liquid is flowing, one thing we can say here is that because it is a constant rate, right, so pretty much the flow is steady, then I can assume that at any part, let's say, here's one point, here's another point, here's another point, here's another point, any point that I look at, I will find, some quantity that will be constant. And that constant is what we call a flow rate. So this flow rate Q. The flow rate Q for a, laminar steady state, let's say flowing liquid will always be the same. And then the flow rate is a product of the velocity of the liquid times the area. Let's say if I do a cross-sectional area, right, and then as water molecules are moving, right, so that's basically the flow rate, how fast the water moving through that area compared to this area. Even if, let's say, the areas might be slightly different, but this product will be the same. That means velocity will be exactly, velocity times area will be exactly the same. So for example, see, this is clearly bigger area than, let's say, over here. So then area 1 is not equals to area 2. But if I'm doing the flow rate, which is V1 times A1, so the velocity over there times the area 1 will be equal to exactly the velocity of, 2 times area 2. So that means you might have a different areas, different velocities, but their product will be exactly the same. And it's very important equation. This is known as the equation of continuity. And it always can be used to calculate the water, let's say velocity of the water whenever the, let's say, system goes from, one type of opening to another. So let's say if you have let's say a tube like this, and then it goes and, a different one opening here, let's say A1, another opening here, A2, you can then use this equation to calculate how fast it's moving here compared to how fast it's moving at the, when it's going through the area 2. So we can actually, look at it in terms of this. Velocity is not the same, but the flow rate is the same. That means the product of velocity and the area. All right, so let's look at, an example here. What area must a heating duct have if air moving 3 meters per second along it can replenish the air every 15 minutes in a room of volume 300 cubic meter? Assume the air density remains constant. All right, so we're basically given 2 points. One is in terms of, let's say, certain opening here with which we're given as area 1, right? So let's say here's the opening, area 1. And then this is the V1, which is the air is moving through that point 1. Okay. And then the second is basically, let's say, the room wall, right? Which is, has area 2. So then what we need to do here is we need to find uh, what area must a heating duct have. That means we want to find A1 uh, if the air is moving 3 meters per second along it, and it can replenish the air every 15 minutes in a room of volume 300 cubic meters. All right, so that means we need to then use this continuity equation, and we can basically treat then this room as a large section of a duct, and we can think of then air equal to the volume of the room as passing by point 2 in this given time of 15 minutes. So we don't really want to keep time in terms of minutes. So 15 minutes, we're going to convert it into seconds, where then 1 minute is 60 seconds. So to get this as 900 seconds, so that means we get the time. And then we can then look at in terms of then this V2, since we're given this length L2, so V2 is equals to the distance over time. Okay, that means, it's basically then L2 divided by time. All right, so this is, V1 is given as 3 meters per second. And then we can take this V2 to be then this distance over time, so L2 over T. All right, so using the continuity equation, where we can say flow rate at point 1 is equal to the flow rate at point 2, which means then A1 V1 is equal to then A2 V2. Then I can say then A2 times V2 can be written in terms of then L2 over T. Then rearrange and just solve for the A1, which will be then A2 times L2, then divided by V1. V1 times time, so there's also time. Now, what is A2 times L2? Well, that's area times length. That means that's just basically the volume. So the volume, input it like this, divided by the velocity times time. So then that's what we're given, right? We're given volume, which is 300 cubic meters, then divided by the 3 meters per second, that times 900 seconds in terms of then the time. So then area 1 will be equals to 0.11 square meters. And that's how we can calculate then this area. Okay. All right. So continue with another, a principle, another equation. So this is known as a Bernoulli's equation. So this one, by the way, let's say if I kind of go back here, this equation works is continuity equation, right? So let's say when you have a, let's say a tube that kind of goes like this, so changes the opening like that, right? So for example, this is then A1, this is then V1, this is A2, then this is, let's say, V2. Now, one thing we have is this. So for example, flow rate is the same. That means A1 V1 equals to then A2 V2. So for example, then if I'm looking at V2, then this is basically A2 over A1 times V1, right? So kind of rearranging for the V2. One thing you will see here is this. Because area 1 is bigger than area 2, so let's say area 2, so area 1, let's say, is double area. Area 1 is 2 times area 2, right? It's basically, twice as big as area 2. It's probably bigger, right, in my picture, but let's say it's double of the area 2. Then one thing I can see here is, sorry, yeah. So then one thing I can see from here is that I actually made a typo here. Sorry. If I, rearranging, that means I have to divide both sides by area 2. So it's A1 over A2, like this. So that means V2 equals A1 over A2 times V1. But because A1 is equals to 2 times A2, so it's 2 times A2 over A2 times V1. A2's cancel out, then I get 2 times V1. That means V2 is equal to 2 times V1, which means here is the water going to be moving faster. Why? Because it's a narrower, tube. And that's always going to be. So when water goes from a larger opening to a smaller opening, it always speeds up. Okay. That means you can see right here's the opening, so this is the region where basically the opening decreases. So then it goes from larger opening to a smaller opening, then it's actually always going to speed up. If, for example, it goes from a smaller opening to a larger opening, so let's say this is point 0.1, this is point 0.2, again, it is moving faster at the smaller opening and it's moving slower at the bigger opening. Again, because of the flow rate, right? So remember, you have to compensate. So V1A1 equals V2A2. For example, if the area 2 is smaller, then V2 has to increase in order to compensate so the product is still, remains constant. All right, so now we're also going to talk about then why does it happen? Why does it speed up or slow down? And this has something to do with basically the pressure difference. So the Bernoulli's, equation kind of, teaches us, shows us that there is basically a change in velocity because of that, work done, right, by the fluid as they move from one end to another end. So the idea here is that there is a pressure, right, the force one due to the pressure at point one. And let's say here's at point two, then there's a F2 is the force 2 due to the pressure at point 2. That means you basically have, there's a force at both ends, right, point 1 and point 2 in opposite directions. And what we have here is eventually, right, then you're going to look at in terms of the whichever side, right, whichever end, point 1 or point 2 has a greater pressure, then the rate or the flow going to be then following, along that direction. That means if at point 1 you have a greater pressure, that means then the liquid, right, then will be going from point 1 to point 2, because it always goes from a higher pressure to a region with a lower pressure. Okay, and this is basically have something to do with delta K plus delta U is equals to a work done by, by this force, right? But this non-conservative force, which is basically when it's being pushed. The idea is that Bernoulli's equation is just nothing but the conservation of energy equation, where again, what we do here, whenever there's a mass, we replace with density times volume, and we kind of like rearrange everything. So then we talk about here, like let's say this point 1 is along, like let's say y1, and then point 2 is some kind of y2. So there's also the height difference, so there's a potential energy change. And since there's a kinetic energy change, because let's say opening 1 and opening 2 are different, there's a basically change in kinetic energy and change in potential energy, and that's because there's a work done by this force that pushes the fluid from point 1 to point 2. Okay, so that means in a way what we can do here is this work done is due to the fact that there's a difference in pressure. Okay, and rearranging everything, then we end up with the conservation of energy equation, where we're saying that this is, energy at point 1, which is the pressure 1 plus 1/2 rho v1 squared plus rho gy1, which is basically, in terms of the kinetic energy and then potential energy, and this is contribution from the work done at point 1, and this is then kinetic energy, potential energy, and contribution from the work, at point 2. And then what we can say here is that product of the pressure 1 plus 1/2 rho v squared plus rho gy is basically the same for both sides at both points, point 1 and point 2. That means this product, right, of pressure plus 1/2 of the density times volume square, velocity square, or the speed square, plus rho gy is equals to constant. This is known as Bernoulli's equation. That means we can take that, point 1 and point 2, and then assign, let's say, y1 here, and then y2, and then look at in terms of the speed 1, speed 2, pressure at 1, pressure at 2, and then connect all of those things together in this one giant equation of the Bernoulli's equation. It's not necessarily that bad. So this is the kinetic energy contribution, potential energy contribution at point 1, kinetic and potential at point 2, and then this is the basic difference in the pressure. That means what is pressure 1 compared to pressure 2. All right, so let's look at then a few examples. Okay. So water circulates throughout a house in a hot water heating system. if the water is pumped at the speed of 0.5 meter per second through a 4 centimeter diameter pipe in the basement under a pressure of 3 atm, what will be the flow speed and pressure in a 2.6 centimeter diameter pipe on the second floor 5 meter above? Assume the pipes do not divide into branches. All right. So I guess you can think of, like, let's say, here's a, at the basement, and then this goes to, let's say, what is it? Second floor, right? And we're told that let's say we're going to take this in terms of the basement to be our point one. So this is y1. So we're told that it is moving at 0.5 meter per second. That means here the speed one is equals to 0.5 meters per second. And it is 4 centimeter diameter pipe. Okay. That means that, in a way, I can say then, then the radius one is then 2 centimeters, because the 4 centimeter diameter, then you get the radius of, a 2 centimeters. And then at the, a pressure one is then 3 atm. Then when it goes to the, a second floor, so we're going to take this to be 0.2, then what we get here is we're given that it is 5 meter above. That means I can say y2 is equals to 5 meters. Well, I can say then y1 is equals to 0. And then I know that this is a 2.6 centimeter diameter. That means, I can say then R1 is equals to 1.3 centimeters, that, in terms of radius of that, cross-sectional area. And what we want to know here is what is the speed and the pressure. So what is V2 and what is P2? Okay. Now, we have pretty much two unknowns. So then if I write down this equation for the Bernoulli, which is P1 plus 1/2 rho V1 square plus rho GY1 equals P2 plus 1/2 rho V2 square plus rho GY2. It seems like, okay, so I have one equation but two unknowns. What do I do? I can't really solve it with this. But remember, we have another equation, which is continuity equation, because those 2 points are connected. That's why it's important to say it doesn't divide into branches. So then we can assume that flow rate Q1 is equals to Q2, which means A1 V1 is equals to A2 V2. All right, then I can solve for V2 from here, which is A1 over A2 times V1. So then I can say it's pi times R1 square over pi times R2 square times V1. So the canceling the pi's, I can solve for V2, which is, I can even keep everything in centimeters. So it's 2 centimeters over 1.3 centimeters, the quantity squared, right? Because each one is squared, I can just do it like that. Then times V1. And I can calculate basically the velocity 1. And again, you can see, right, because it's a smaller opening, it has to be moving faster. That's basically by, looking at in terms of narrower opening, faster moving speed. So then speed is indeed 1.2 meters per second. So that means now I have one of the quantities. Then if I go back to this equation for the Bernoulli's equation, right, the only thing I don't have now is, pressure, a pressure 2. But, I can simplify this a little bit by canceling this, because y1 is equals to 0. And unfortunately, that's the only thing I can cancel for now. But then everything else, I can just basically just do the calculation. I can say then P2 is equals to, then move everything to the, to the other side, right? Basically rearrange. So it's then P1 plus 1/2 rho, then becomes V1 square minus V2 square, then minus rho GY2. Okay. And then from here, then just basically calculate, plug in everything, right? All the values, right? So I have pressure 1, which is, 3 atm. I have V1, I have V2, and then you can just basically, the density, it's water, right? So it's 1000 kilogram per cubic meters. So plug in everything to calculate P2. Now, what to expect for the P2? Well, remember one thing. Since the water goes from point 1 to point 2, it always goes from higher pressure to a lower pressure. You should expect P2 to be less. And if we calculate, we will get this to be 2.5 atm. Again, you know, because the volume, because the flow is from point 1 to point 2, it always goes from higher pressure to lower pressure. So the second point in this case, because second point is the final destination, always should have a lower pressure in this case, and that's what we got. All right, so there's sort of like a special case for a problem where, let's say, you are talking about some kind of container that has areas that are really large. So let's say, for example, here we have a container where it's open, right? So to atmosphere, and then what we have here is, you can see, right? So this is basically fluid coming from a spigot on an open tank. Now, because this is A2 and this is A1, and you can see, right, there's a really big difference between them. You can say then, in a way, the water here, let's say, right, not really flowing. So then you can take this to be V2 equals 0. So let's say whenever you're considering, for example, also let's say ocean surface or a lake surface or something like that, you can take that actually to be zero velocity. Okay. Now, also, what is, let's say, for example, pressure 2? Well, pressure 2 is atmospheric pressure. So you can say this is 1 atm because that surface 2, right, that point 2 is open to the atmosphere. How about pressure 1? What is pressure 1? Well, that also open to the atmosphere, right? So that means pressure 1 is also equals 1 atm. Then, for example, then what will be the speed of the water coming out of through that opening? Well, what I will do then, I will again use the P1 equals, P1 plus 1 half rho V1 square plus rho GY1 equals P2 plus 1 half rho V2 square plus rho GY2. Well, I can cancel P1, P2 because they're exactly the same. V2 is equals to 0. Then all I have here is 1 half rho V1 square equals rho GY2 minus rho GY1. I can even cancel all the densities. And then I end up with V1 is equals to 2 times GY, so 2 times, let's say, GY2 minus Y1, because V1 is squared, then take the square root. And that's what we have. This is known as Torricelli's theorem. That means that equation that, basically simplifies to just V1 equals, and think like this. Even if I take this to be Y1 equals 0, all I need is just a height difference, then this becomes just square of 2GY or 2GH, right? This is basically exactly the same equation that we have used before for the velocity of, let's say an object at the bottom of an incline or something like that, right? The lowest point. So it pretty much comes down to exactly the same equation, because remember, this is conservation of energy, right? So you end up with, something like this. All right, so this is a long chapter, and one last thing we have then at the end of this chapter is the elasticity. So we talked about fluids. Now we're going to the solids. So now we're going to talk about how you can take a solid object and be able to, let's say, apply force. And when you apply force, some solid, most of the solid actually do have some elastic properties, and then they can basically change, right, their shape a little bit. So we kind of talked about, right, elastic, elasticity of the object, right? When there's a force acting on it, it can change its shape. So suppose you clamp one end of a solid rod while using a strong machine to pull on the other end, as you see in this picture over here. So here the figure shows that graphically the amount of force needed to stretch the rod. Okay, and this equation you probably have already recognized, F equals K times delta L. It's basically, this Hooke's law that we have seen, right? So it's force equals, some proportionality constant times the delta L is just basically the change in length. That means if you take this, climb it at one end and apply force on the other end, it can actually be, stretched a little bit, right? To that, this distance delta L. So then this graph represents, this is sort of like, let's say, the elastic region where you are pulling it to the right, and it's basically stretches, 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 stretches. And then this is like elastic limit. Okay. That means from here then starts deforming. And then at some point, then it can actually break. So that's basically the breaking point. That means you want to go from, let's say, in terms of being able to stretch or compress or change the shape so that it can go back to its original shape. Then you have to be in this, basically in this region, right? In the elastic region. Apply force in such that that force is not too strong, and it basically within that what we call elastic region. But then if beyond that, then you are basically deforming the system, deforming the object until you can, at some point you completely break it. So what we can look at here is, remember, when you pull, you are pulling, exerting force at some area A. Then this F over A, which is force acting at that area A, is, remember, there's nothing but, actually pressure, right? Is proportional to the ratio of delta L over L. That means this F over A is proportional to then delta L over L, change in length over the entire length. And then the proportionality constant is then known as a Young's modulus. So this Y is the Young's modulus. Okay. So this quantity on the left side, F over A, is known as a stress. Okay, so this is known as a stress. And the units are, newtons per square meters, right? On the right side is delta L over L, which is, unitless because both meters, so then they can cancel out. So this is known as a strain. It's a fractional, increase in length. So, and then one thing we can say is we say the stress, which is F over A, equals modulus times strain, which is delta L over L. Then in a way, right, so the Young modulus, not like that, like this, is equals to then strain over stress. Oh, sorry, stress over strain. Or basically F over A over delta L over L. So this is the table for some of the Young modulus values, right? Aluminum, concrete, copper, mercury, and things like that. So you can see, right, that concrete is a widely used building material because it is relatively inexpensive, and with its large Young's modulus, it has tremendous compressional strength. All right, so here's concrete, right? So it's cheap and it has a large Young modulus. All right, so then we also can see, right, bulk modulus. Okay, so we're going to talk about that also. But let's look at, this example here first for the Young modulus. So we have a 1.6 meter long steel piano wire, has a diameter of 0.2 centimeters. How great is the tension in the wire if it stretches 0.25 centimeter when tightened? All right. So, well, it's a piano wire, so something like this, right? Or maybe like bigger, let's say like that. So it's a, the length here is 1.6 meter long, and it's a diameter, or the, like a radius of 0.1 centimeters. Okay. So then it says, how great is the tension if the wire is stretched 0.25 centimeters when tightened? That means, it's, let's say this delta L is 0.25 centimeters. It stretches by this much. All right. So that means, if I convert this, so it's going to be, 0.25 times 10 to the negative 2 meters, right? Because 100 centimeters is 1 meter. Then from here, I can use this, equation where then F of t, right, in this case, over area, and equals then the Young modulus over then delta L over L. Okay. So probably one thing we can do here is even just let's say the ratio of delta L over L, we can even keep it, let's say, in centimeters or in meters, doesn't matter. So for example, then we have a steel piano. So we come back here and then look at, okay, so for the steel, it is 20 times 10 to the 10. That means Young modulus is, again, 20 times 10 to the 20, 20 times 10 to the 10. Okay. So by the way, the units are newtons per square meters. Okay. So it's newtons per square meters, because remember, this is dimensionless. So the Young modulus has to have the same unit as on the left side, which is newtons per square meter. Okay. So then from here, we just solve for the tension force, which is, Young modulus times delta L over L, then times area. Okay, so it's then 20 times 10 to the 10 newtons per square meters, then times, what I'm going to do, I'm going to keep it in centimeters, point 0. So 0.25 centimeters over 160 centimeters, right? Because 1.6 meters is 160 centimeters. And times the area, which is nothing but pi times 0.1 times 10 to the negative 2 meters squared. So then I can calculate this tension force to be 980 newtons. There you go. So that's basically the tension force. All right, so then the last thing we have here is the volume, stress and strain. And basically then there's a bulk modulus. So this is basically when you have a, not just a linear length, but, entire, like I said, the volume. So the volume stress applied to an object compresses its volume slightly. That means, we have then this change in volume when there is a, forces acting on it. So in this case, then F over A, which is that, the stress, right, acting on the object, so which is basically the pressure, is proportional to the change in pressure, change in volume over the volume. And the proportionality constant is then bulk modulus. And that means F of A equals negative times B times delta V over V. Okay, it's negative because it basically compresses generally. When there's applied forces, right, it's going to just kind of compress. So the B is known as bulk modulus. The negative sign ensures that pressure is positive number. Okay, so now one thing we can do here is, if I go back here, you have then in the table I also have the values for the bulk modulus. So you can see, right, so in terms of then the bulk modulus, again, it's in Newton per square meter, and then you are given the values for most of the type of, let's say, material. Again, you don't have to memorize any of these values. They either will be given to you, or, let's say, you're going to have to be asked to calculate that. But, most of the time those values will be given to you. You don't have to memorize. You don't have to write down in your formula sheet. Even if ever there's a question, this constants will be provided to you. All right. Anyway, so those are basically, in terms of, like, let's say, what happens with the solid object, right? When there's a force acting on it. So basically, when there's a forces acting on a fluid, right? There's a pressure. So we looked at the applications of that, and these are the application when there's a forces acting on a, let's say, the solid object. All right. So then that concludes this chapter 15 and basically this class. So these are all the material then for the final exam.